So I'm going to start again with directional square functions and prove upper bounds today. But first, I want to go back to the positive effective inequality for a second. I remind you what it is. The L4 norm of a function supporting in frequency in the delta neighborhood delta square neighborhood of the paraboloid or the sphere in dimension 1 satisfies this decoupling inequality. Okay, maybe let me do the notation for the sphere this time. If you partition the delta square neighborhood into delta square rectangles, then f theta is just the Fourier restriction, smooth or rough, whatever you want. F hat phi p theta, or this is the sector theta. Okay, and we of course have the inequality f, same assumption. We have the inequality fp equals less than or equal cp sum over theta f theta squared 1/2 p for p equals 2, right? This is just finally overlapping cover. However, we cannot interpolate. Why? Because this assumption is not preserved by interpolation. Okay? So, but by interpolation, you can, given we have done this, given that we know that the operator p theta f theta satisfies a vector valued bound of this type okay, log delta. And okay, we have proved this inequality essentially the first day, where t theta is a multiplier adapted to is a multiplier adapted to theta. Okay, then we conclude that f, under the assumption if f is supported in frequency in the delta square neighborhood, fp, this is equal to suitable sum of t theta f theta. And what you do is you take a t theta that is essentially 1 on the support of f theta. Okay. P, and then you apply you apply the estimate, and the decoupling is served. Okay. So we know this for we know this. Now, it's a nice question to see whether, I mean, it's not known whether this estimate holds without dependence on delta when P is different from 2 and 4, okay? Whatever you end up doing, you try to do is gonna give you this loss. Okay. So question, can the log loss be removed? Okay, I have no insights on this, but I think it's a nice question. And there's a paper of Carberry where he mentions this question. Okay. Okay, back to forward estimate. And let's remind ourselves what kind of square functions we might want to treat. So the setup is we have n directions. And a priori are arbitrary. Okay. And then n collections of frequency regions which let's say omega j, which may be tiled by almost rectangles, by pairwise disjoint, and collections of pairwise disjoint. By pairwise disjoint or finely overlapping. Omega j, almost rectangles, pointing along Bj and Bj perp. Okay. So this is the most general way to describe this setting. The examples were, let's start from this. Take disjoint cover of this is the example before with delta equals 1 over n. Okay. Each of these rectangles, as described before, is pointing in a direction Vj, which is roughly e to the 2 pi I j over n. Okay. And along Vj, you have delta squared, and along Vj perp, you have delta. Okay, so in this case, omega j is rectangle delta Vj perp, say, cross delta square Vj. And they have this joint. Okay, so this clearly falls into our frame. The second example was to have n-disjoint bonds rooted at the same point in frequency. Okay, so this is omega 1, this is omega 2, and this is omega 3. How am I going to tile this with almost rectangles? I'm going to use little Pei theory. And omega 2 is the union for k from minus infinity to plus infinity of some omega jk. Okay, where if Vj is the center of the cone, central direction of omega j intersection S1, okay, then omega jk is 2 to the k Vj times 2 to the k aperture of omega j along Vj curve. Okay, so this is your omega jk. Here I have, okay, so the resulting decomposition is essentially this, right? This is the relevant cone, and then I have this, and I have this, and then I have this, and then maybe I have this. And okay. And then I have the Rubel square function, which also falls into this category, but I'm not going to repeat. So the typical result is the following. It's the sum over j equals 1 to n, the sum over k, and then I have, how did we call them? T, P. Well, now today I called these regions omega instead of P. So now I write T omega j. P is less than a constant that will depend on n only, and then okay, for 2, P, 4, and then we have endpoint type results where the L4 norm, the same square function, is controlled by Kn4, Kn41, F41. Okay, that's the Lorentz norm. You can also say that this is the same as having controls for of the type F infinity measure of E to the 1/4 for all F supported, not in frequency, on the set E. On E. Okay. So this is a so-called restricted type testing. The target space is still at 4, but the domain space is strictly smaller than before. Okay. Fine. In all of the examples I have drafted, and here let's say here T omega JK is a smooth cutoff to omega JK. Maybe there is only one omega JK for each region omega J, like in this case. Okay. This is the simpler case where this sum is not there. But in this case, we said that via little Perry theory, the conical square function can be reduced to this case. Okay. So, and yesterday, in some work, we saw in one of the cases, in this case, that Kn has to be greater than log n to the power 1/2 minus 1 over p. Okay, and in fact, our work allows us to get this constant in all of these estimates. So yesterday we saw with the counterexample based on the Kakeya set that Kn cannot be better in this case than log n to the 1/2 minus 1 over p. And in fact, main theorems show that this is the case. Okay. Then we come back to maybe main open questions. Okay. So the method is mostly homogeneous with respect to the setup. Okay. So it's based on time frequency analysis. Uses wave package. Okay. Let's review what I mean by that. Okay. So the idea is to decompose use Fourier series or Gabor series on each T omega F. Omega here is one of your omega JK. Okay. So let's, before I'm gonna give rigorous definitions of ties and of uncertainties and everything. But what did we say? We said that T omega is concentrated on the dual rectangle. Okay. Is concentrated on the dual rectangle of omega. So at first approximation, I could think of this as F 1R star, 1R star. And to have something in L2, I have to divide by R star. Okay, this equality is wrong, not correct. Okay, but what is correct is using Gabor series, we can write this as sum over all R prime that are translates of R in the sense that we of R, and then we pick an orthonormal basis that still stays supported on omega, but this is roughly the indicator function of R over R over R, 1/2. It's not really. The additional thing is that this guy has no frequency support, but you can use Gabor series and keep this orthonormal decomposition having not only localization on R, but also frequency support on omega. Okay, so this is the idea. And then what you're gonna, okay, then more or less T omega F squared then is gonna be what? Sum over all, okay, this is a prime. This is the sum of a prime translates of F phi omega cross R prime squared, indicator function of R prime over R. Okay, because if I take the absolute value of this and I pass the square inside, roughly these guys have disjoint support. And so, you know, I can pass the absolute value inside, ignoring, I mean, I can pass the squares inside, ignoring the sum. So this becomes F phi omega cross R prime squared, and this used to have oscillation, this used to have frequency support. Now it's just this guy squared, because I have removed all the cancellation. Okay. So this is the idea. Now let's be a bit more precise. So let's say a tile is a set which is the Cartesian product of Rs cross omega s, where omega s is a rectangle, almost rectangle, of scales L omega s along Bs perp cross with omega s Bs. Okay. It's an almost rectangle with some scales along a certain direction Bs perp. Rs is a reciprocal rectangle, it's a dual rectangle. So it's an almost rectangle of scale L Rs Vs per with Rs Vs per cross L Rs Vs. Okay, and what do you have to have? You have to have that the length of omega s times the width of Rs is 1, and the length of Rs times the width of omega s equals 1. Okay, so they are reciprocal rectangles. This is Vs, this is Vs perp. More or less, this is omega s. And of course, I got it wrong. Vs perp. This will be Rs. Okay. So that's a tile. Of course, to each omega jk in R decomposition, we associate all the tiles such that omega s equals omega jk, and in particular bs is going to be vj. Okay. And these are the, I mean, of course, rs here will be a translate of omega jk star. Okay. This I'm going to remove. Okay, so we can convert our we say phi s is L2 adapted to the tile S if what? The support of phi s is contained in omega s, and then the way one should look at this is the essential support of phi s in space is contained in S. Okay, and F2 not known. Okay, the rigorous way of saying this is that if AS is the linear change from -1 squared to RS, then the function RS 1/2 phi s composed with AS. Okay. Imagine that this is RS, and this is -1/1. AS does this. Okay, let's call this function, I don't know, psi s. Psi s has the following, let's say, psi s decays like this. For all alpha. Okay. So it's basically having polynomial tails away from the rectangular S. That it's convenient to avoid defining the center of RS and all the scales. It's convenient to say, okay, if you rescale the function phi s to live on the unit cube, then you get a function, you get a bump function. Okay, you can write this out. Okay, so these are adapted functions. I guess maybe keep this in mind. I'm gonna tell you what kind of operators we're gonna go and examine. So by the reasoning I sketched, you can study. Let's say that you are studying the bounds of the square function that I erased before. T omega jk f squared 1/2. P, this is controlled by this square function. This is the sum over all tiles. Let's say this is the sum over all j equals 1 to n. And this is the sum over all tiles in S of omega. Okay, that was also the sum. These are the S such that omega S equals omega. And then here we have f is squared, 1 is over is. Okay, because I have basically I have shown that the square of this is essentially the sum. And so here I'm basically summing over all possible omega jk in the decomposition. Okay. So the set of tiles relevant for each square function is the union over all j equals 1 to n of Sj. This point along Vj. And each Sj in this example, specific example, is all the tiles. This is the union over all k. Sj. Here, omega s equals omega jk. Okay. So to discretize, for instance, this square function, you have the sum of the squares of the coefficients times the indicator to this omega jk. You make it correspond. What is the short? This is the long direction. You make it correspond all of your, and this is the long direction. And this is they don't look great this way, but they have to point along this direction. You have, this is omega star, and then all the transient. Okay. So to avoid writing all of these summations, you can just write the square function like this. S in S, F by S squared 1 S. Okay, this is the square function we're going to establish. So S comes from J from n different families of tiles. They point in different directions. The remark, which is yellow because it's important, the way we have constructed our set of tiles, we have that the collection of tiles as sets is a pairwise disjoint collection. Pairwise disjoint. Why is this a pairwise disjoint collection? Because the omega regions are disjoint, right? Look at the omega regions, they're all disjoint. Okay. The R regions, so if omega is different from, if omega s is different from omega, let's say if omega s is equal to, the point is, if omega s intersection omega s prime is different from empty, then they must coincide. But if they coincide, Rs is going to be different from Rs prime, in fact, disjoint. Because with the same omega s, you must have different Rs. Okay? So with this remark, it should not be it should not be a surprise the next lemma. Okay? If I sum over all tiles my coefficient, this is less than or equal and the L2 norm of F. Okay, why? I mean, if this would be obvious if you have two different tiles S is different from S prime, right? Because then, I mean, this would be this sum equals F by S. Okay, before I don't want to repeat things 3 times. So, do you guys agree that if I had perfect orthogonality, then this would follow? Mi chiami se non sai che sto facendo lezione. Non mi chiamo mai. Okay, but okay, let's give a proof of this fact without cheating, without the cheating. Okay. Okay, proof. Assume bilinearity of the L2 norm of F is 1. Okay. Then and call the quality we want, which is I don't know, let's call it W. W F by S squared. Okay. What is W? W is equal to the scalar product of the function F by S by S. F. Okay. This is just by expanding. There's nothing to prove here. Right? Take the scalar product of this, with that you get exactly this. Okay. Good. Now this is less than or equal than the L2 norm of F, which is 1, times the L2 norm of okay. Well, then W squared is less than or equal the L2 norm square of this guy. Right? Which I'm gonna write. This is sum over S prime in S. Let's use like S and T. I don't want to write it right. F by S by S by T, F by T conjugate. Right? This is by just taking the integral of this guy squared, multiply it out and integrate, you get this. Okay? Now, okay. This, I'm going to prove that the supremum over S in S of the sum of phi S phi T is uniformly bounded. Okay. And this is not difficult. Why? Because phi s, phi t is not zero if and only if omega s is equal to omega t. Because the frequency supports are disjoint or coincide. Okay. And so, well, then if it means that S is equal to R cross omega S, and T is equal to R prime cross omega S, and R prime is equal to some translate of R. Okay. Now, a simple computation shows that in this case, phi S phi T is less than 1 plus K to the power to minus power to 1 minus M, which is sum over the K in Z. Okay, but then I'm gonna, here I have two summations and symmetry. I mean, so W becomes squared, becomes less than or equal than sum of F phi S squared plus F phi T squared over 2. Okay. Phi S phi T. This is the most stupid Cauchy-Schwarz ever. I don't know, it's young, right? And then here you have two summations, S and T. But fix S and sum over T using this result will give you, and symmetry, this will give you that this is controlled by F phi S squared, which used to be W, and you're done. It's a very easy orthogonality statement because essentially the supports are disjoint. The frequency supports are disjoint. So of all the tiles, what really count in this supremum of the sum, in this sum, are the ones that have the same frequency interval as IS. But they are really, there is essentially only one tile that can be. Questions? I have, before the break, 10 minutes, so I will leave this lemma, erase the proof, erase everything, and explain my second lemma. It is a little bit more difficult. By the way, this is the first thing you should prove when you discretize some linear operator. Okay, when you use time frequency analysis, you started from, this is equivalent, if you think about it, to the L2 norm for the square function that you construct as a model. If your square function was bounded in F2 and the model you construct is not bounded in F2, you have already discretized it. Okay, and this was it was difficult to make this mistake. You probably don't do this mistake, but okay.
Okay, if you have a situation that you don't have the disjoint frequency components, this will happen. I mean, this can happen.
Well, something else has to save you.
Yeah.
Okay. Well, no, because there has to be a different reason why the operator you start from is F2 bound, not pure orthogonality. Okay. Okay. Now, let me give a definition. We say a collection of, okay, let Rj be the collection of rectangles that are equal to some Rs for some S in Sj. Okay. We have J collection of rectangles. These are the rectangles that come from types in Sj. So these are like points along Bj. Okay, and I'm going to use the notation R for the union of all the J, and then I'm going to say that the collection rho, maybe rho is better. Okay, rho is subordinated to the collection P E. P is a collection of rectangles in a fixed system of coordinates V, P, V, E, P. Okay? V is fixed. It's a collection of rectangles. We should probably, it doesn't matter. Yeah. I'm going to draw one such collection. This is one rectangle. This is another rectangle. And this is yet another. For some reason, I have drawn it disjoint because only pairwise disjoint collection of rectangles really matter for this definition. And then subordination means that for all elements of rho, there exists, if you want, a unique element of P with R containing P. Okay, so this is the collection P, and the collection rho is this. Maybe I'm going to do them in a different color. So, okay. This is an element R of rho. This is another element. This is another element. And here are some more elements. Okay. Do you guys understand which one is the subordinate? So the yellow one is the subordinated. Is it a difficult definition? No. It is cumbersome to write? Yes. What is simple is, oh, okay. If I draw the picture, you understand in a second. Okay. So the lemma, Ma2 maybe there. Lemma. Local almost orthogonality. Let E be any set, a measurable set. any, and V, a collection of tiles with and the assumption is that the collection of rectangles, the tiles in V is subordinated to some collection P. Okay, so suppose that these rectangles in my drawing are actually rectangles RS for some tile in V. Okay. Then the statement, then this has nothing to do with it, it's a different lemma. Then the statement is that the sum of S in V of F by S squared is less than the L infinity norm of F squared times the union of P. For reasons of not repeating myself 100 times, the union of a collection of rectangles will be called the shadow of that collection. Okay, before the proof, let's give the wrong proof. Before the break, let's give the wrong proof. After the break, I give the correct proof. Okay, this is not really surprising as a lemma. Why? If S appears in this sum, RS is contained in P for some P. So, right? So I can, in particular, RS is contained in the shadow of the whole collection. Okay? Well then, and this is the wrong part, F, well, then the scalar product of F with pi S can be replaced by the scalar product of F on the shadow of P pi S, because the support of pi S is contained in RS, which is contained in the shadow of P. Okay? Okay, if you make this replacement, then lemma 1 show that the left-hand side is bounded by the L2 norm of F, indicator of the shadow of P squared, which is equal to the shadow of P times the L infinity norm squared. Well, this is equal, it's less than that. Okay, so this is the trivial statement. What is non-trivial is to get rid of the tails. Okay. Let's talk in the minute. Questions, comments? Too slow, too fast, fastish? And the next dilemma is nice. So when we write, I mean, we're friends. Let me do this. We know each other a lot. I will this
there was, Francesco, there was this. Vectors being area, right? When you were saying that, I mean, you have the L for norm, the L for estimates, L for estimate, the Korthoff-Hefferman L for estimates from the square function. Like, and then you have the trivial true estimate.
Yeah.
Then you were saying you cannot interpolate.
I can interpolate that.
Because why?
Because the interpolation, that's not it's not a linear operator. The map that maps F to the vector. Yeah, okay, it is a linear operator, but
I mean, I just remember that you were saying something like it does the condition that
it has to be defined on interpolation is about products. It has to be defined on the whole empty space. It's not defined that estimate is not true for the whole empty space.
because it's just for function of that
Yeah.
support.
Yeah. So you have to insert an operator that may basically make any of your function a function in the empty space.
Then like with you get some log estimate, log loss.
Yeah, you get a log loss because your vector value. So what you can do is you can then interpolate the two estimates that you have, true, but then for this operator. But okay, it's a nice question because you say, okay, I don't want to interpolate, man. Like interpolation is for like numbness. You can like go inside and do it, but it's very complicated. So.
El tuyo es blanco, entonces.
I'm trying to log in and that's working. I don't know how these people manage to log in.
Because you're logging in the wrong. I think we logged in the wrong. There are two different. Okay, let me move this lemma a little bit so it's visible on the screen. It's about like here. Let's update the statements a little bit. So F infinity squared, shadow of the collection P. And then here I have lemma 1. And this I can just write. Now everything is visible, even if it's a bit small, but it's, I can read it. And I'm old, so you guys are young, you should be able to read it. Okay. So we need two tricks for this lemma. The first, okay, try to remember what it means to be subordinated. If you don't, there's a picture. Okay, this proof uses the lemma from Journe's paper on multi-parameter P of 1, which is the following. Let P be any collection of rectangles in a fixed coordinate system. Okay. Let's define the slight enlargement of the shadow of this collection, which is the set where the strong maximal function of the shadow is greater than 2 to the minus 10. Okay, by the boundedness in any space, L2 for instance, the measure of the shadow star, this is an aside, but we will use this, is roughly the same as the shadow. Okay. And for each P, let UP be such that if you enlarge P by 2 to the UP, you still stay in the shadow star. But if you enlarge it by a tiny bit more, you don't stay. Okay, maybe I can do a picture. This is the collection of rectangles. It's a bit random. Okay, this is shadow star of P. And what happens is that this is 2 to the U, some rectangle. This is 2 to the U plus 1, some rectangle. Then U is equal to UP. Okay. So basically, this UP measures how much you have to enlarge the rectangle to get out of the shadow star. It's always greater than 0, if you want. It's always greater than 1, in fact, with this constant. Right, and then, okay, the rectangles with the same U are essentially disjoint. That's what it's saying. If you sum over all of the rectangles P in P with the same U, they are not only essentially disjoint, they are, well, okay. They are not really essentially disjoint, but you only lose 2 to the minus U. Shadow of P. Okay. Of course, this is the union, this is the sum. In principle, this can be very big compared to the union. Because these rectangles are random, they can overlap, they have multiple eccentricities, we have no control. However, if you fix the embedding quantity, this UP, then, okay, yes, they're not essentially disjoint, but you're only losing. Okay. There are more precise versions of this. Okay. So this is one trick. Another trick is the localization trick. This has really no proof. In the sense, it's just basically stepping down the definition. Given, let's take one of RP, and well, this is a center plus the length of P along some EP, some vector E, which is the same for all P, in fact, cross E1, so let's do E1, W of P, E2. Okay, this is just saying how does P look in these coordinates. Let's define a polynomial in the coordinates. I'm going to call it poly P x. This is the polynomial that is 1 plus x 1 minus CP1 over LP to the power 200 plus x2 minus CP2 WP to the power 200. Let's put squared. Okay. Like this is a polynomial, okay, that vanishes on the center of P and decays like the distance from P. in either rows. Okay. Now, if the lemma is if S is such that it's a tile like this, okay, then phi tilde S P poly P times phi S is adapted to S. Okay. Basically, what happens? Take a tile whose spatial interval is contained in P. Okay? Phi S is an adaptive function to S. In particular, its Fourier support is contained in omega S. Now I take phi S and I multiply it by a polynomial. What happens to its Fourier support? Does not change. Multiplying for a polynomial by a polynomial in space means taking derivatives in frequency. Okay? So I'm not going to change the Fourier support of phi SP. Okay? But I am now, okay, so as far as support of phi S P tilde hat is still in omega S. What I have to check is that phi S tilde P decays away from the rectangular S. Okay. But look, I am making phi S tilde P grow as I go far away from P, but this guy decays much faster in both directions because the scales at which it is oscillating is decaying are shorter than the scales of P in both the horizontal and the vertical direction. So you can compensate the growth of P by the decay of phi S. Okay. Of course, this is not going to decay as fast as phi S. It's going to decay at an order which is 200 times, 400 times smaller. But this guy has an order that is 1 million. Now this guy has an order which is like 500,000. I don't care. Okay. This is a trick that is always used, always, in time frequency analysis. But when is it used? Is it used when the rectangles of the intervals have the same, I mean, the cubes have the same coordinate system? The difference here is that you don't need the coordinate system to be the same. Okay? As long as basically the projection of this interval and of this interval in the directions of V, Vs and V per S are big enough. One unit of this has to be compensated with 1 unit of distance in Vs or Vs prime, whatever you need. Okay, so this is true. And now we can prove the lemma. So the proof of before was almost correct. I can assume that F is supported away from shadow star of P. Right? Why? Because the piece of F is supported from shadow of P star. I can prove that it was wrong. Okay? The difference is I'm gonna have shadow star P instead of having shadow P. It's the same, okay? Now, using Journe lemma, it's enough to prove that the S in S with S in B with RS contained in a given rectangle P, F by S squared is controlled by 2 to the minus 50u F infinity squared P. Okay. Why? Because if I have, well, where U is UP. Why? Because if I fix U and I take all the UP, all the P with UP equals U, then I can sum and I get 2 to the minus 49u times the shadows of P. Then I sum over U. Okay. So this inequality plus Journe lemma gives you everything you want, because you can first sum over P with a fixed U and then sum over U. The sum over P with a fixed U is gonna give you, well, not shadow. It's gonna give you 2 to the U. And it's compensated by 2 to the minus 50u, and so then you can sum over the embedding parameter. That's how Journe lemma is always used. You have a collection of tiles of wave packets subordinated to an open set. Okay, that's how, I don't know, multi-parameter per function are found. Okay, or John Nirenberg, multi-parameter John Nirenberg. It's proved this way. You don't say, okay, let's take maximal rectangles, let's take all the supports of the wave packets that contain a given rectangle, and then we use it. Okay. Of course, what you have to be able to do is to obtain some decay. Okay. Okay. Now, this is my target, remember. But I'm gonna multiply and divide by poly P inside. So this is equal to F chi poly P or poly P inverse. And here I have phi S tilde P squared. Okay. And now this function is, here I can use what? These are adapted. So I can use that lemma. Well, this lemma was proved for a fixed adaptation, but you know, if you decrease the adaptation a little bit, it doesn't change. So I'm going to bound this by the L infinity norm of F poly P alla to the minus 1/2 infinity times poly P F2 to the minus 1/2. Okay, well, clearly here I have bounded this by F poly P inverse 2, 2, which then I control in this way. But now, on support of F, which is a way poly P inverse is very small. Well, so this is like F infinity, poly P infinity, but on support of F. Why? Because this is P, this is 2 to the UP, and here is the support of F. Right? This is when we use that 2 to the U P is still not outside the shadow star. Okay? Therefore, your distance, the distance from the support of F to P is like 2 to the U times P. And therefore, you decay polynomially, this is less than 2 to the minus 100 U. Okay. And now, if you integrate this guy, this is like integrating 1 over 1 plus x over LP plus x1, x2 over WP to a large power. And so this returns 2 to the minus U, well, 400 U, what do you say, 100 U times F infinity squared. And this returns P. In the paper with 100 position is useless. You can just use this. Polynomial P is like an infinity thing away from P, and so it has the integrals you can compute. Okay, so we have proved the lemma. Nice. We're ready for the next definition. I don't need Journette anymore. So at this point, the analysis in the phase plane is finished. There is no more eyes in the phase plane. What comes is the following. Let definition. Okay, I already defined what the collection value are. We say AR. Recall that AR is indexed by all the rectangles in our tiles. These rectangles are actually come from J equals 1 to n different possible orientations. We say that this is a Carleson sequence. Normalized in infinity. If this sum is finite, I'm going to call this the mass of the Carleson sequence. Okay. Maybe let's call it A. Let's give it an A like this. And whenever you have a subordinated collection, rho, this is less than the shadow of the subordinated collection. Okay. Whenever rho is a plausible collection and rho is subordinated to P. Okay. So Carleson sequence. This is a little bit less stringent than being a biparameter Carleson sequence in a way, because subordination means something special. However, these rectangles can be from different orientations. So it's a little bit like product Carleson sequence. Okay. You guys,
Stronger than bi-parameter calculus.
well, no. Well, it's each condition is not by parameter calculus. It's similar. If you put the fact that you can change the orientation in a number of ways, yeah. Okay. Associated to a Cartesian sequence, we define the operator Pr of x, which is the balayage. So it's some sort of embedding. 1R over R. Okay. Let's give a few examples of these Cartesian sequences. Okay. And okay, let's first give the real example. So consider the maximal operator MRF of x supremum okay.
It's just, I mean, the definition of the Cartesian sequence, this is the definition of the mass of the.
Mass array is finite. The formal definition is a formal condition, right? Okay. Okay, then the weak type norm of MR is comparable to the T R of A L2 over e to the 1/2 for a suitable collection A, Cartesian sequence A and set E. Okay. Basically, the balayage of the Cartesian sequence linearizes the L2 is the L2 to infinity adjoint of okay. So why? Well, and in general, MRF to infinity. Let me explain this very quickly. Is MRF 1e over e 1/2 for a suitable set. Okay, this is the principle that the weak L2 norm is actually adjoint to the restricted L2 norm. Okay, but now if you linearize the operator, the maximal operator, this is basically the sum over all rectangles. Well, it's equal 1 over each to root. Sum over all rectangles of F R. Let's say F is positive, and then 1 VR. Okay, 1e over R. Yeah, okay. Let me write it this. Let me write this average as f integration against one other, where dr is the set, is those guys in R such that the chosen rectangle by the supremum is equal to R. Okay. Very nice. Now I can write this as F against sum over AR, 1R over R, 1 over. Okay. And then, you know, F is in L2, and so to control this, I can give F L2. And this is the T RA norm. I just have to define what AR is. Any idea? AR is this integral. I mean, if you look at what's going on, AR is the measure of the intersection VR. Okay, what's the mass of this collection? If you sum over all R, this VR are disjoint sets, therefore the mass is equal to in the example. And this is just disjointness, pairwise disjointness, so it's very trivial. So this is the first example of balayage of a Cartesian sequence that, you know, comes up naturally. The second example is, and that's the beautiful idea of the paper, in my opinion. This is like, okay, maybe we don't write the paper. Another example. Yeah. The example is the following. So look at the sequence. So R is really R equals RS for some tile. And AR is the sum over all tiles which have rectangle R of F by S. Unfortunately, you see that the square function we care about, which I don't know, I probably call it in some way, the square function F squared used to be the sum over all S tiles of F by S squared 1 RS over RS. Now, if you just apply the definition, this is equal to sum over all rectangles AR 1R over R. Okay, so the square function is the balayage. Square of the square function is the balayage of a Cartesian sequence. And so the L4 norm of the square function is the L2 norm of the square function. It behaves like the maximum function. The adjoint to the maximum. Let's say again. They are both balayage of two different Cartesian sequences. So this and this have the same behavior. Basically, all the theorems I'm going to state end up like this. Delta SF squared 2 behaves like MR 2 infinity. Well, okay.
For restricted F.
Well, for restricted F. when well, okay, there's this the correct way of seeing it is that this behaves like T star well, TR 1E. Okay, so if you know a little bit of the theory of the maximal function, this is really not, you can't say anything. They are both the same object. Now, the nice thing is that we have a theorem that deals with both at the same time, because it deals with balayage of constant sequences. But okay, just to understand what we're gonna end up getting, this is MR, L to infinity. Okay, this I believe this is L log n. Okay, if you have a collection of rectangles, like in our examples, okay, so you have n different collections of one parameter rectangles in a fixed coordinate system, and this equivalence is a result of cuts from Duke roughly 25 years ago. Okay. And therefore, we understand the four norms of the square functions we care about in the restricted sense are log n to the 1/4. That's all there is. Okay. So this principle kind of, I could finish here and not detail the equivalence, but I have time, so I will basically state the principle, because there is a little bit of necessity of ideas. Okay. This theorem deals with, has not a frequency analysis, doesn't even have maximal functions, directional maximal functions. Okay. I will tell you why, what brought us to this point, but let A be normalized Cartesian sequence. Okay, and suppose that for all collections, you know how the maximal function behaves near L1. It behaves polynomially in 1 over p minus 1. Okay. Then I'm gonna help you read this, parse this in example. There is some gamma. It's telling you that basically the weak LP norm of each fixed coordinate collection. So this is not about directional maximal operator. It's about what happens for each direction of rectangles. Okay. Suppose this has the weak, if it's just a collection, a one parameter collection of rectangles, then this has the weak one bound, just like the little maximal operator, because you can bound it by essentially Fubini and one-dimensional little maximal function. So there is no blow up as p goes to 1 of these norms, and the gamma is equal to 0. Okay, most common case, and in all of our examples, we'll think about it a little bit, gamma equals 0. But there are cases in which gamma can equal 1, and we don't know of cases where gamma equals 2. Okay. In fact, gamma is at most, it's at most 1. It could be that for some collection you have gamma equals 1/2. Okay, who knows? Half parameter collections. I don't know what. But in our our examples fall into this. Okay, then this balayage of Carleton sequence T R of A in F2, I write the square, is less than log n times log n to the power gamma, the mass of A. Okay. Let's look at this example, this in the example of one of our square functions. Okay.
R is now the union of.
Well, R used to be the union of the RJs from the beginning. It's been erased, but R is
Okay, that is the RJ are the, okay, those are J.
Okay, so let's look at this case, which is the easiest. So this is like the forward Cordoba vector. Rectangles each direction. Rj is, I mean, this is even easier because there is only one family of rectangles that all have the same shape. Let's take this guy that points more or less vertically. The short direction is vertical. So these are your rectangles Rj. They are even pairwise disjoint. So this is omega j, these are Rj. Here, clearly, gamma is equal to 0 because even, I mean, the maximal operator here is really an averaging operator. Huh? Okay, that's good. What about, there are other cases, but what about this case, which maybe was worrying, right? Could be worrying. This omega jk point all in the same direction, vertical, say, and have all the same eccentricities. So this guy will have these rectangles. Okay, now the guy above it, this is omega j k plus 1, will have rectangles that have the same eccentricity and point in the same direction, but they're smaller because this one is bigger. So like this. And these are not a one parameter. These are, you know, by a change of coordinates, this is the Hardy-Littlewood maximal operator. Was just rescale. And so gamma equals 0. Well, then I had the Ruby di Francia, and there, no, you can have, depending on what is the characteristic of the of your frequency rectangles, you could have gamma equals 1. Because you end up getting a two-parameter collection of rectangles in each fixed direction. Okay, as long as you have, you know, these, well, these are not disjoint, but imagine that your omega jk pointing in this direction are these guys. And then you can have disjoint and longer. And they don't have to have the same, maybe, you know, actually the correct example would be longer and thinner. Okay. So this is a two-parameter collection of frequency rectangles. It gives you a two-parameter collection of spatial rectangles in the same code. And there, by the rating or by the Zygmund theorem, what's it called? boundedness of the product maximum operator.
Jensen security.
Jensen theorem, this gamma is equal 1 in. Okay. So these are the examples. And so for our square functions, we gain what? We gain the estimate in all three cases, we gain the same estimate. We gain the estimate delta S subordinated to an indicator function, but it has to really be sub-indicator, not indicator. Because, you know, if AR comes from a sub-indicator function like this, then the mass is 1e, and I mean, just divide by the L infinity norm of f, and it goes outside. So what you end up getting is 4 is equal to PRA 2, which is bounded by log n times the mass, which is p. And that's the inequality we have proved. And the other exponents, so we always prove the L4 case, and the exponents followed by interpolation. Okay? So in particular, this gives you the aspect function in LP behave like, okay, what do I interpret? Interpret 1/4 with 1, 1/4 at 4 with 1. And so you get the exponent that you get interpreting this is log n to the 1/2 minus 1 over p. I'm writing 1 over p equals theta over 2 plus, well, theta over 4 plus 1 minus theta over 2. You find out that theta is 1/2 minus 1. Theta over 4 is 1/2. Okay. So I'm not going to prove this this principle because it's complicated and long and has several steps. But in some sense, it's not super new because these balayage of Carlson sequences have been used by Netskatz in his proof that the maximal function has the same bound. Okay, so what we did was remove the fact that this comes from linearizing a maximal operator. Allow for the assumption, this assumption to be, it was implicit in his proof, which was only written for one parameter collections essentially. And now it's explicit and it's used in this quantitative way, okay? And then essentially it's the same proof. Okay, so you should probably look at that paper because it's written after Netskatz's paper, and so it's easier. We wrote all the details. The nice thing about this principle is that, well, I'm just gonna mention this, but this extends to codimension 1 problems in all dimensions, in all ambient dimensions. Okay, so you could be in a tree where your directions, now you can give me n directions in S2, and your collections are no longer rectangles, but they are objects that, you know, are called plates. The plates have a codimension one singularity. So you're allowed to have n-1 long directions and one short direction. Okay. The relation to these vectors is that you are telling me what is the normal vector to the n-1 long directions. Okay. These plates are dual to frequency objects, not almost rectangles. Well, okay, yes, almost rectangles, but the dimensions are, these are tubes, are dual to tubes along the direction V. Okay, where this is 1 over the width of R, and this is 1 over the length. Okay. So basically you can repeat most of this paper, most of this, or all of it, by looking at square functions that are tiled by cubical regions in Rn. Okay. So for instance, you could consider not cones, but you could consider, now I erase this. A Rubio differential type result in Rn. So if we're in Rn, we have n directions, B. Okay, and now for each j, let omega jk be disjoint over j and k cubes pointing along Vj. Okay. Picture. Here's a collection of things that point along V1. Let's make one that is bigger. They are disjoint. Each of them has an adaptive multiplier. I don't know, I call it omega kj. This is like T omega jk. Now I have another direction, but I still keep the disjoints. Okay. And yet another direction, maybe this. Okay. I can do a square function of these, and the bounds are going to be the same. Well, yeah. Okay. So in fact, this is a different paper with me and Yanis. 2021, and it's similar results but different proofs are appeared by Gan, well, I have to put names, Shengwen, Gan, and Shukun. Similar, like maybe 2022 or now on the art. Okay. They have square. We have, and they also have square function results for conical or cubical regions in Rn. Okay, and the blow up is similar. It's similar. It's a network. Okay. Okay. Let me mention what the biggest question is. Okay, that we couldn't really settle, and then we go home, I think. And tomorrow we see some applications of these square function estimates, and maybe we start with the Gutmann-Zhang paper. I'm not very optimistic, but maybe we can start with the setup. So the biggest unsolved question in our paper is definitely whether this substitute, you can we can use the methods in our paper with the estimate. Okay, let's say we have this one. Okay, we have the secret type. Now, if you use the interpolation, the stupid one, okay. So this implies that via how do you call that argument? So you're using
Interpolation.
some sort of interpolation, but it's not really well. Well, it's interpolation because you know, L for one is in between L2 and well, L4 is in between L for one and L2 in a sense.
I usually do the dualize it to see.
Okay, it's done also in many papers of Bourgain, of Ciprian. Is but this is not sharp. Or we don't know if it's sharp. So that's a big question. I tend to think that this is okay. It was very advantageous for us to have some indicator functions when we proved the kind of measure estimate. On the other hand, you know, there could be some substitutes to that. Okay. So the only place where we really use it is that I mean, okay, for an L4 function, I wouldn't be able to conclude anything. I have to conclude for a sub-indicator function, which is like a logarithm away. Well, okay, then maybe if you're more careful, you can do things in a slightly different way for L4 function. And that's probably, you know, someone has tried, or, you know, I haven't really tried too much. But, well, now that we have all the forward estimates, it would be nice to use these methods to prove backwards estimates. Because you see, the backwards estimates for diff, of course, for p between 2 and 4 strictly. Okay? Because you see that our methods do not use weighted extrapolation, like, you know, the first day I showed you the estimate for the vector valued multiplier, okay, the one that we record today, multiplier from f into TPF, FP to TPFP. So this estimate relies on the vector. I mean, this vector valued estimate relies on the weighted theory of each TP and then on the maximal theory. Okay, so it's weighted for TP and then the maximal for all. We don't use this operator in our assumptions. We regrow its boundedness somehow. So maybe our methods are not going to be dependent on interpolation like these methods. We don't, for this estimate, we specifically never use any interpolation. Also in the sense of like, is there any part of the argument where you do use interpolation? And the answer is no. For this one, of course, for that one, yes, but if you worked hard, you could probably prove this directly without interpolation. The norm between the L1, yeah, because this is the L2 norm of the balayage, is the 4 norm. The L1 norm of the balayage is trivial, so you could think of LP norms for P between 1 and 2, which would be the same as this estimate.
This estimate is somehow of, I mean, even CAD's estimate is interpolated. It proves it just at the critical index.
Yeah, but if you try really hard, you can prove it. Well, no, it's just it's simpler because these are integer values. But somehow TRA1 is trivial and TRA2 is this, and then you can.
Well, it's a John Nirenberg in a quality function. You go from 2 to you bound, it's like a reverse.
Yeah, you bound 2 to 1, so you could bound like, so in principle, there is no interpolation if you want.
Improvement
What?
from the restricted with type, from the 4-1 to 4 estimate to the 4 to the strong 4 estimate, with loss of additional powers of the logarithm.
Yeah, it's easy to do it on the It's easier to do it on the dual, which is weaken is L for thirds to weaken for thirds. And then you have a trivial estimate on L1 by losing powers of N.
Okay.
And you have a trivial estimate above the. And you
The thing, how this implication works. Yeah, it's just level set. You know, this, you can use it, you dualize, which is easier, and you use the certain level estimate until, you know, for infinity is good until a certain point, and then L2 is good until another point.
The other estimates you interpolate are trivial, just N and whatever.
Yes.
Then you optimize the different way, like you do some kind of splitting like in Marcinkiewicz, but in two different levels, let's say.
And this is just another power of logarithm.
You lose 3/4 exactly because of the dual. So, and it's written very carefully in the paper of Cyprian in proceeding to the MS.
Yeah, it's really.
I think this argument was first used by this guy.
Number?
Yeah. Or that's what I assumed at first.
Was a lot of stuff.
Anyway, maybe you might want, because tomorrow is to finish sharp.
Tomorrow you have to finish early, not sharp. Why? Because we have a seminar and it's actually 2 sessions.
What does it mean?
It means that it would be very good to finish like a quarter to.
Yeah, I can do it.
I would say max a quarter. Because we need a small break. Yeah, then we'll have 2 talks. Yeah.
Oh, really?
Yeah.
Who's talking?
I don't know.
I'm gonna just go and prepare my next lecture.
I mean, just maybe you do less time. Yeah. That's an idea.
No? Yeah. But I can do like 3.
Or faster.
No, I'm gonna do like 3 to 3:40, then 10 minutes, then like 10-minute break, and then 3:50 to 4:30.
30.
35. Well, if I do like blocks, although it's still doing 2 blocks of 45 minutes, it do like 2 blocks of 40 minutes. Like, you know.
But you've not done 2 blocks of 45 minutes, you've done 2 blocks of 55 minutes.
It's 10 past now.
Okay, we have finished no, I finished on time, but maybe 1 minute.
The thing is, if you have a function in L4, how can you construct the Carlos?
Well, I mean, like,
you need a stopping time argument, because you need to pretend it's bound. So you need something like a Calderon decomposition, let's say. But this is a directional problem, so.
you have to redo this estimate and define, like, I mean, subordination becomes a little bit different, right? That's
No,
you
I
can
mean,
sort of.
the estimate you wrote with the after Zurnel lemma.
Yeah.
Okay, if F is not bounded, it doesn't work.
Well, you kind of make it bounded, right?
Also
Also,
to make it bound, but how do you make
also, it doesn't work really. I think it does. It kind of does. It kind of works. Like it would look at the estimate. You just need you need some condition on the maximum function of f, basically.
Yeah, so you need
Like this p has to be stopping times of.
yeah, exactly. You need that the R's are stopping rectangles, but
No,
these
P's
are
are stop. P's are stop.
yeah, the P's, okay. But they might be two parameter, first problem. And they are in directions, second problem. So you will lose from that. Even if you make it work, you will lose because the corresponding maximum function has a loss. And maybe in the end you lose as much as you by doing this trick. It's not great. Because if you define stopping, let's say rectangles, the constant where the level has to depend on log n.
These are stopping for they're not stopping for the whole guy. I mean, even though if you use the stopping things on L4, it's probably just 1/4 loss. So maybe.
Look, I think that the best thing one can expect is log n to the 1/2 at the end point. I don't think you can expect anything better.
They said it follows from our paper, like. Okay, we like this.
Or it's not obvious.
It's not obvious. They make the mistake of using again the trick in a wrong way. They think, okay, I'm at 1/4, I'm gonna lose 1/4 instead of lose 3/4. Very silly. So the result is actually stronger. I mean, for like uniformly distributed directions. This is the nice thing is that this can be any directions, which is like much more difficult.
Okay, I don't know why you said cube regions. We do conical regions. But
Well, no, that's a bit. We do conical regions
yeah.
by what? Okay, but that's like.
And you split them with a little belly, and then you get this almost cubes, let's say.
Yeah.
I mean, you do a partition on the sphere.
Yeah, but conical, the analog of conical is these cones are wedges in higher dimensions, so you cannot treat them.
No, because dimension 1, there are honest cones.
Yeah, and then honest cones, then yeah, fine. That's a good dimension. One thing is I wasn't thinking straight at that point. So but what I wrote is correct. That's included in the table. You're complaining for nothing, basically.
Same with two conical regions. So that's it. Also, this kind of condition includes the product, because every collection that is acts parallel is subordinate to itself. So it includes colors. It's just not the full, let's say, take any open set and then sum. That would be the directional, I don't know, full. I don't know what it means. Doesn't make any sense. I don't know. Before, huh? Zeros. And after all. I was trying to think that now. I mean, if you manage to do some kind of spotting dynamics, it's a bit sketchy. And it's forward sort of dynamic. Okay, dynamic is not a. What you have to work with product theory, so you don't have. What are your stopping rectangles?
Well, but no, you keep using Journal now. You are going to